All right, how's everybody doing? Professor Bryant here with a mini lecture. This mini lecture is going to be covering part of Chapter 2 that we were not able to get to in class for Module A. Expectation is that you'll be responsible for this material as it pertains to that particular module. The PowerPoint that we're going to be looking at today is from Chapter 2 as well. This is about halfway through the PowerPoint. On slide 25 is where I'm going to start this. Okay, so the periodic table, as it is organized currently, is very systematic, and I will be placing a video over the organization and kind of the current periodic table and where it came from, and who helped design it. But it's organized systematically based on the types of elements that we have found and how they behave, particularly their characteristics. But the arrangement is from left to right in order of atomic number. So as you increase the number of protons, you're increasing the atomic number, you are increasing the size of the element, but you're also changing its identity, and by changing its identity, you're changing its characteristics and how it behaves. So we've already talked about the atomic number, which is at the top of the square in the periodic table, and underneath the letter, the symbol, that is the average atomic mass, and we talked a little bit about the average atomic mass and how to calculate that. We're not showing that on this particular slide. So, okay, when we're talking about rows, we're talking about the rows from left to right. We're going to call those periods, and there are generally 7 periods on your periodic table. That means there are 7 rows left to right from top to bottom. And then the columns from left to right, we have a total of 18 of those. Columns are up and down. We have a total of 18 of those, and those we call groups. And within a particular group, you're going to find very common chemical properties and characteristics. So very similar elements are going to be found in a given column or in a given group. And that leads us to the idea, the concept of periodicity. We have a repeating periodic type cycle as we move across the periodic table, because as we move across, we'll eventually come back to that same group in the next period, in the following period, and then within that same group, we see similar characteristics. So as you can see here on this slide, helium, a very non-reactive gas, is in the noble gas. Neon is the same non-reactive gas, and if we go back, we see that helium and neon are above and below each other in the periodic table. So that is periodicity, and that is the same for your metals as well as your non-metals. So we notice this repeating pattern of reactivities, and therefore we know that these are in the same group generally, and if they're in the same group, they have the same characteristics, and we have names for groups, and the 5 common names that you're generally going to see associated with a group are going to be group 1A, which is the very first column all the way to the left, and those are called the alkali metals, and those are the elements such as lithium, sodium, potassium, rubidium, cesium, francium. Now, one thing we need to realize is that hydrogen, although it is on the left of the periodic table, it is not a metal. It is not a metal. It is a non-metal. It's just located there for design purposes. The alkali earth metals are in group 2, which is the second column to the left, and that second column to the left contains beryllium, magnesium, calcium, strontium, barium, radium, and the name, and you need to know these names based on a given element. If you see an element, you need to know the name. If you see the name, you need to be able to write down an element. Group 6A, which is actually on the right side of the periodic table, you see group 6A is here, and that contains our friends oxygen, sulfur, selenium, tellurium, and polonium. and we call those the chalcogens. Beside them, we see the halogens in group 7A, and halogens are fluorine, chlorine, bromine, iodine, and astatine here in group 7A. And then last but not least are the noble gases, and these noble gases are highly unreactive as a group, and these are helium, neon, argon, krypton, and xenon here. Okay, so now that we've kind of got some names and we know a little bit more about the periodic table and what each group and how we call them, I also wanted to mention and talk about where different elements are and what makes them a metal, a metalloid, or a non-metal. So if something is on the left side of this kind of stair-step division line, then it is considered a metal. So all of the light brown color elements here are considered metals. So if you have been given an example of a element and ask if it's a metal or non-metal, you need to find this area in the periodic table, determine if the element is to the left. Remember that hydrogen is our exception here just because it's up in the top corner. Metals, hard, shiny generally, solid except for mercury, and they have common characteristics, but you at this point you just need to be able to recognize, is it a metal, is it not? Okay, on the right side of this staircase line, in the greenish kind of color, we have what we consider to be non-metals. Non-metals are generally softer, not shiny. In some cases they're gases and liquids, but the non-metal group is very small compared to all of the rest of the groups. It's smaller than the metal group. And then on this stair-step line are the elements that kind of exist right in between the metals and the non-metals, and these elements are considered metalloids. They're purple, and metalloids are kind of the best of both worlds, right? The best of both worlds. So here's the description of the metals: shiny, conduct heat and electricity, generally solid except for mercury. The non-metals on the right again, with the exception of hydrogen, they can be solid, they can be liquid or gas at room temperature. And then elements on the staircase line in the purple, except for the aluminum, which is a metal, and then polonium and astatine, which are polonium's a metal, and then astatine is a non-metal. Their properties depend on the environment they're in. They are generally somewhat conductive depending on what you use them for. That's why silicon is a great semiconductor, because it can do whatever you want it to in the environment that you put it in, whatever you kind of mix it with and bond it with. So these are the different parts of the periodic table, and really quickly we're going to do some example work here. And the example work here is going to be taking 3 different elements, their full names, and then determining the type of element, whether we're metal, non-metal, or metalloid, and then the group. And if they have a group name, what is the group name? So here I have a periodic table. The first one I have is cadmium. So if we find cadmium, we see cadmium's here, right? Cadmium's here. It is a metal. It is a metal. So the type, we're going to go metal. Okay, group names. All of the 5 common group names, this does not fit in any of the common 5 group names, but I will say that if it's in the middle of the periodic table, like cadmium, from zinc to scandium and anything below that, we're talking about a transition metal, what's known as a transition metal. We'll talk about those a little bit more as we get further into the semester. Okay, antimony. Antimony is SB here, and it's on our staircase line. It is a metalloid. It is a metalloid. And it is in one of our common groups because it is in group, it is not in one of our common group names either. It is not in one of our common group names. So antimony, we won't have to worry about a group name. It is just a metalloid. And then selenium is here. It is in our group 6A. It is to the right of the staircase line. So it is a nonmetal. Sorry. Kind of long. It is a nonmetal. And is in 6A. So that makes it a chalcogen. Makes it a chalcogen. Okay, so there's a couple different examples of something, of the things that you kind of need to be able to do for this particular portion of the content. All right, so once we know if something is a metal, a non-metal, or a metalloid, then we need to know how it behaves with other elements. We need to know how it does its bonding, its interaction with other elements. And a bonding is what gets you a compound, right? By definition, compound is a molecule that has more than one different type of element. And to create a molecule, you have to form a bond. To create a bond, you have to start involving electrons, right? Electrons. So when we're talking about chemical formulas, the little small number you see in a chemical formula, that tells you how many numbers of atoms of that element exist. And it's always the subscript to the right. It affects the element to the left of that number. And when we're talking about molecular compounds versus ionic compounds, which is what this portion is covering, molecular compounds are almost always composed of molecules and contain nonmetals. So in all of these different scenarios, if you notice, hydrogen, oxygen, carbon, all nonmetals, these are all molecular compounds here. These are not all molecular compounds. Water and hydrogen peroxide and everything below it is molecular compounds. Hydrogen and oxygen are elements. Those are elements. So here we have some the 7 diatomic molecules that you have to remember. You just have to remember these. Hydrogen does not exist by itself. Nitrogen does not exist by itself. They're all diatomic, as you see here in this slide. Oxygen, fluorine, chlorine, bromine, iodine. You just have to remember those. Now, we already talked about empirical and molecular formulas in class. Structural formulas, when we get into drawing of Lewis structures, we're going to talk about the 3-dimensional shapes of our molecules, so we're not worried about that right now. But now we need to talk about what happens in ionic bonding. So I'm going to cover ionic bonding in this video, and then in a separate video, I'm going to cover molecular compounds, nomenclature, and bonding. But now we're going to focus on ions. So here we have a cutout, essentially, of the periodic table, the part that we're interested in, and we see that our group 1A, remember, alkali metals, 1A, alkali metals except for hydrogen. Group 2A, alkaline earth metals. Group 5, 6A, chalcogens, and 7A, halogens. Now, all of these are the common ions that are formed from any of these elements. All right? The way I have chosen to represent this on a periodic table, and you can do so on your own periodic table in your notes, again, is write the type of ions that each of these columns generally produces. And remember, aluminum is the one that matters here because aluminum is the only metal in this situation that we need to be worried about. Boron is a non-metal, so we're not really dealing with a +3 charge when we're talking about boron. We're talking about aluminum. But -3, -2, -1, and this pattern exists for most of all of the molecules that we're going to be talking about when we're talking about ionic bonding. Again, you won't have these on your reference materials when you're taking your assessment, but it's good to have them in your notes to just get used to looking at it. Okay, so to become an ion, become a charged element or charged particle, you have to lose or gain an electron, meaning that the atom itself must pull in an electron from somewhere else or give one away. What we notice that Cations, C-A-T-I-O-N-S. Generally speaking, I use the T to remember that it's a plus. Cations are positively charged and they have to lose an electron or more than one electron. Metals are generally the guys who are forming cations, as you can see in this example, in this picture here. Hydrogen can form a positive ion. It is not a metal, but it can form a positive ion. Anions mean that it has gained an electron, and if you have gained an electron, then you're going to have a